Hey guys, just to let you know, this lesson is in collaboration with Flip Academy, a free online platform for all of your GCSE, A-Level, IB and CBSE revision, out now on web at www.flip.academy, and also as an app for Apple, iOS and Android. It really is better than all the other GCSE platforms out there. It covers all the topics in great depth and has an app that you can download your courses on and use offline. Hello and welcome back to Flip Academy. So this is the next video in our CIE A Level Maths series, and today we're going to be covering vectors, which is primarily a paper 3 topic. So this is everything you need to know for vectors, so let's get into it. We've got a lot to cover. So first off, we just need to know the standard notations, which you may have covered a bit in GCSE, you may have seen before. So if you have a two-dimensional vector, you can just put x and y on top of each other, which is the GCSE kind of notation. But you can also write that as xi plus yj. And these j's here, so the I, j and k, they all mean the same. They're just basically giving you their unit vectors. Okay, unit vectors in the x, y, z direction respectively. So effectively, the x value might be, let's say, 4. I means you're going 4 in the x direction. 3j would be 3 in the j direction. Negative 3k would be minus 3 in the z direction. Okay, so it literally just provides the direction. You also have like a vector name, so AB for instance, with an arrow above it, which is a position vector. So, and lastly, which is not one that you'd ever use for writing, is they also put vectors in bold. So those are the different notations you can have. Now, of course, you can't write in bold in pen, so I would recommend always using like an underline or an arrow on top, or the I, J, K notation, or of course the column notation. So we also need to be able to carry out addition and subtraction of vectors, multiplications of a vector by a scalar, and interpret these operations in geometrical terms. It's quite a lot. Then also calculate the magnitude of a vector, use unit vectors, displacement vectors, and position vectors. This is a lot of stuff. So we're going to take it step by step. So if I start with the magnitude of a vector, and what we'll do, the reason why I'm going to start with the magnitude is I'm going to show you the geometrical terms at the end and addition at the same time. So the magnitude of a vector is signified by having essentially, so for example, you might have a vector 3, 4, and we can call that A, right? So the magnitude of the vector means you just have these two parallel bars next to them, okay? So these two vertical parallel bars, okay? And that symbolizes the magnitude. And all you do is you take the square root of each term squared. So 3 squared plus 4 squared, okay? And if it was a three-dimensional vector, so you have 3, 4, and 1, you'd add plus 1 squared on the end. Okay, so it kind of looks like Pythagoras, which it pretty much is. You just take each of the components, square them, add them together, square root them. So in this case, that would be square root 25, because 3 squared is 9, 4 squared is 16, which of course equals 5. And just so you're aware, technically it would be plus or minus 5, but think about it, a magnitude is a size. Okay, you're saying how big is the vector. If I say the size of something, it's always positive. Okay? So the way you can think of it is if I said, how long is this line? I'd hope you'd never say to me it's negative 5 centimeters long. You'd always say 5 centimeters long. So magnitude is kind of like a length in that sense. It's always positive. Okay? The next thing I'll talk about is unit vectors. So I did mention them earlier, but you also need to be able to work them out, but it's not too tricky. But essentially, a unit vector is just the smallest vector. It's the smallest vector that provides a direction. So I mentioned earlier with the I, J, and K, they provide, they're the smallest vectors that provide direction in the X, Y, and Z axes respectively. Provides a direction of a vector. But of course, so for example, you might have a vector that is quite long and it goes not just in the X, Y, or Z axes, but it could go in all three of them, right? You could have vectors like 1, 2, and 3. So the unit vector for that would be the smallest possible vector, so it has a magnitude of 1, okay? And it would be pointing in the exact same direction. So essentially it's parallel to the vector and it has a magnitude of 1, okay? So if I scroll down a little bit, it always has a magnitude of 1. Okay? And the way you work this out, and the kind of notation for it is, let's say you had a vector, so we call this u for instance, then u with a hat implies it's a unit vector, is just the actual vector itself, okay, so I should actually put a little arrow on top of that, divided by the magnitude of that vector. And hopefully that makes sense. If you divide each component of a vector by its magnitude, then it will give you something that will have a magnitude of 1. So that's all you need to do. It's not too tricky. We do have some example questions coming up, so don't worry too much about it. The next thing you need to know about is position vectors, which you should be fairly familiar with. So position vectors describe the position of a point, shockingly. Okay, so they describe the position of a point relative to the origin. So we always take these from the origin itself. Okay. So as an example, what we can do here is, if I had a triangle, right, and we had two other vectors, so two other points, so we have A and B, and we have O here, then the position vectors you could have as A and B. By the way, just so you know, this is actually also covering the addition for geometrical terms. So if I were to work out what A to B is, that will give me a vector which looks something like this, okay? Where AB would just equal minus A plus B, okay? Which you can also write as B minus A, of course, right? So the two position vectors we have here, so I think I actually labelled one of the vectors wrong earlier. This would be a displacement vector, and the two position vectors we have here would be A and B, so we would call those OA and OB. Okay, those are position vectors because they describe position relative to the origin. So I think earlier on I said this was a position vector. That should actually be displacement, so my apologies there. And displacement just tells you how like a vector moves, so it's the kind of distance between 2 points if you'd like. Okay, so again with this, if you subtract vectors, the way you would draw that is you'd have them be kind of tail to tail or tip to tip, so you draw them like this. So the subtraction AB here, you write that as OA minus OB. Sorry, the other way around for that one actually. So yeah, so the other way around. So OB minus OA for this sense. Okay. So when you have a subtraction like that, you just draw a line that's kind of, so you draw the vector as normal, but then you put the two tails touching each other, and then you just draw a normal line that goes between them, and that will give you your actual vector AB if you're subtracting two vectors. So that covers that in geometric terms. Okay, and just a few other terms that you need to know about. So displacement vector, we've gone through what that is as a vector. So it's basically what AB is in this sense. So it describes the distance between 2 points. However, there's one kind of caveat here. It actually describes the shortest distance between 2 points. And between 2 points. And of course, as you know from either physics or GCSE maths, displacement is a vector, so it obviously does give you a direction as well. And the reason why I say it's the shortest distance is because they're always straight lines. So when we deal with vectors, we don't deal with something that's curvy. It's always a straight line. And as you know, the shortest distance between 2 points is always a straight line, okay? So that is something that you should definitely keep in mind. So now for the geometric description of how addition works, right? All you would do is you would draw them tail to tip. So in subtraction, you draw them tail to tail. For addition, you draw them, so for example, if I had vector B, and then plus vector A, I'm drawing them so that the tip of one touches the tail of the other, and that means my resultant vector here, right, is B plus A. Okay, so subtraction, you put the two tails together, or you can even put the two tips together as well. With addition, you put the tails and tips touching each other, okay? So with subtraction, I could have easily written that where the tips are touching each other for A and B, and I'd get the exact same answer, so it doesn't actually matter. And then of course when you add and subtract vectors, you just add and subtract their components, right? So you add and subtract the I components, the j components, and the k components. Now, for multiplying by a scalar, so I did say we had a lot of notes to go through first, and we do have a bunch of questions, so don't worry, we will go through examples of all these. So multiplying by a scalar, so first of all, scalar is just going to be just a random number. So let's say if we had vector A, and we'll make it equal to 2, 4, then scalar multiplication might be something like 3A. All you do is you multiply the components by 3. So you have 3 times 2, 3 times 4. So in other words, you get 6 and 12. So the way this looks geometrically is, let's say this is A. 3A will just stretch the vector in the exact same direction. So you'd have something that goes out to here. Okay, and that would be 3A. So the overall vector here, the overall line, is 3A, whereas this is A. And it should be 3 times longer, right? In my drawing, it's not exactly 3 times longer. It looks actually about twice as long. But the point still stands. Okay, you'd have a vector going in the exact same direction, but it would be 3 times longer. And this is why unit vectors work, right? So A could easily be a unit vector, and so 3A it gives the direction, right? Because when you times by a scalar, you just stretch in the exact same direction. Okay, should be nice and fancy. Okay, thankfully that's all the notes we're going to do for now. So if we go down to the first question, we have 2018 paper 1. So relative to an origin O, the position vectors of A, B and C are given by these 3 vectors, and again they are position vectors because they have O in them. So if you have O, it's always a position vector. If there's 2 letters next to each other that aren't O, so A, B or AC or BC or something like that, these are displacement vectors, okay? So when you're working out AC, if you remember what it looked like geometrically, which was back here, we would put them tail to tail or tip to tip, and we actually subtract one vector from the other. What we do is we take the first vector, the second vector, and you subtract the first vector from it. So when we do AC, we're taking the position vector for C and subtracting A from it. Okay, that's the way I remember it. If you're unsure, you can always draw a little diagram and have a look. So for example, we have A and C. And so and this is obviously O. So if we draw these out, if I'm working out from A to C, I'm going to go against A. So I'm going to go minus vector A and then plus vector C. Okay, so there's 2 ways to think of it there. You can either just do the second letter minus the first letter always, and that'll always give you the right answer. Or if you draw a diagram, you'll see that you'd have minus the first vector plus the second vector, which is the same as saying second vector minus the first vector. Okay, I said vector so many times it's kind of losing meaning for me now. So we have 3, 1, minus 2. Subtract 1, minus 3, and 2. And again, beware of the signs. When you subtract vectors, you literally just subtract the components. So 3 minus 1 gives me 2. 1 minus minus 3 would give me 4. And minus 2 gives me minus 4 for that question, okay? Nice and easy, hopefully. Part 2, the point M is the midpoint of AC. Find the unit vector in the direction of OM. So again, this is using the exact first point here. So it's the midpoint of AC. So if we work out what OM would be, because it's the midpoint of AC, so it's the midpoint of this, we can say that we'll go from O to A and then plus half of AC, right? So we're going to go OA, so I'm actually going to, no, we'll leave it there. OA plus half AC. Okay, so just again, we're going from O, we're going O all the way up to A, so it's positive, and then we're going to go to AC, and we know what half of AC is, but let's work this out now. OA is 1 minus 3 and 2. and that's a half. And again, I'm going to do these steps really kind of slowly and carefully just to make it make 100% sense. But you can skip some of these steps, that's completely fine. I'm just making sure that everyone's okay. Half each of these values, you get 1, 2, minus 2. So if I add those together, we get 1 plus 1, which is 2. Advanced maths. Minus 3 plus 2 is minus 1. 2 plus minus 2 is 0. So you don't leave it blank, you always put the 0 there. And then if we're finding the unit vector, if you remember the equation, OM with a hat will be the vector OM divided by the magnitude of OM. And again, I'll add my little symbols now for all of this. Okay, so again, just going back up to the previous part. Where was it? Here it is here. Okay, let's go down. So first of all, we need to work out the magnitude of OM now. And I wrote it as the square root of 2 squared plus 1 squared. So that's 4 plus 1, which is, so it'd be square root 5. Again, it's always positive, so we're going to leave it as square root 5. So OM with a little bit of a hat is going to be, and this is the way I would write it. Ooh, almost wrote the wrong thing. If we have OM divided by the magnitude of OM, because I know that we can't divide 2 minus 1 and 0 by square root 5. So for example, if this number was, let's say, 2, right? Then I would do the actual division. So 2 divided by 2 would be 1 minus a half, 0. But when you get a square root, which you normally will, right? Because normally you can't square root numbers and get integers. I would write it like this. So 1 over square root 5, which gives us the divided by OM bit, and then times the exact normal vector again. Okay? Because A, it looks nicer, and B, I don't have to do this weird maths, because otherwise I'll have 2 over root 5 minus 1 over root 5, 0, which is a really ugly looking vector. But again, if it's a whole number, then you might want to actually do the calculation. If it goes in nice and neatly, in general, avoid fractions and decimals. Just leave it on the outside. Nice. Okay. So we have to do the scalar product of two vectors and use the scalar product in problems. So there's two definitions of the scalar product. And I think the best way to do this is to show you is to show you through an example. Okay, there are two definitions of the dot product. The first one is, so for part 3, so with the question, it is using AB and AC from up here. Okay, so I'll give you those vectors now. And if you want, you can go back and work them out, but this is what the vectors should be. So 2, 4, minus 4. And AB is... So again, we know what AC is because we worked it out. AB would be, again, OB minus OA. And again, it's just the vectors from the previous question. So OB is minus 1, 3, 5. And OA, you can go back and check, but I remember it being 1, minus 3, and 2. I'm not that senile yet, thankfully. Which, if I work it out, minus 1 is minus 2. 3 minus 3 is 6. 5 minus 2 is 3. Okay, so the two definitions of the dot product are as follows. So if you do the dot product between two vectors like this, you would write it as so. So minus 2, 6, 3, dot, and then AC. So that was AB, this is AC. And it's actually quite easy. So what you do is you times the components and add them all together. So this is what it would look like. Minus 2 times 2, so the top components, plus the middle components, plus the bottom components. And you do keep the same signs and everything, so it's not too bad. So you have minus 2 times 2 is minus 4, plus 24, which would be 20, minus 12, which would be 8. Again, here's a calculator test, but I'm being a bit lazy. Cool. That's one definition of the dot product, this first one. So if they ever say calculate the dot product, and you have the two vectors, right, you have the actual I, J, K components of them, then you just want to do this. Nice and easy. Sometimes you don't have the actual components, right? Or you want to work out the angle, which it says here. So this is the angle between the two vectors. So the other definition of the dot product is as follows. In this case, it would be the magnitude of AB, or AC, doesn't actually matter which way around you do it, times the magnitude of AC, cos the angle between them. And that will equal also, in this case, 8, right? Because we know what the magnitude equals. We know what the dot product equals. So there's two versions. One, if you have the IJK components and you're just asked to work out the dot product, you times them together and add them up. If you want to work out the angle, or you don't have the actual components themselves, you want to use the magnitude of one vector times the magnitude of the other vector, cos the angle between them equals 8. So what we need to do now is work out modulus of AB and modulus of AC. So mod AB is square root minus 2 squared, so 2 squared plus 6 squared plus 3 squared. The reason why I just got rid of the negative is because I know that when I'm squaring it, it's going to be fine. And that would give me, so 4 plus 36, that's 40. 49, square root 49 is indeed 7. Equals similar thing, so 2 squared plus 4 squared plus 4 squared. Again, ignore the negatives because they obviously don't affect it. So that's 4, so 6 and 16 is 32 plus 2, 4, so 36, that should be 6. So in short, we have 7 times 6 cos BAC equals 8. So we can just work out that the angle BAC is the cos inverse. So again, this is just a simple rearrange. 8 over 7 times 6, which should be 79 degrees. So I have a calculator, one sec. 79 degrees. Perfection. 4 marks. Bit involved, but again, for a CIE question, it's actually not too bad. But let's go on to the next one. Another thing that you should note, by the way, is if you look at this definition, cos BAC. Okay. So if I had two vectors which were parallel, right? Sorry, perpendicular is what I meant to say. Let's not put that there actually. Then the dot product is 0. So dot product equals 0 if the vectors are perpendicular. So we can use this as a test to work out if two vectors are perpendicular. So one way is literally if you times and add the components and they equal 0, you know for a fact that they are perpendicular vectors, which is a pretty handy thing to have actually. And the reason why is because cos of 90 is 0. Nice and easy. 2a, relative to an origin, the position vectors of A and B are given by these two. Cool. The angle AOB is 90 degrees. So they are perpendicular to each other. Find the value of P. Well, it looks like I just gave you the answer. We're going to take the dot product and show it equals 0. So again, dot product equals 0 if they're perpendicular to each other. So let's work that out. So if I do the dot product with 3 minus 6 and P dot 2 minus 6 and minus 7, and that equals 3 times 2 plus minus 6 times minus 6 plus minus 7p equals 0. So that is 6 plus 36 minus 7p equals 0. Move the p to the other side and group them together. So 42 equals 7p. So that means p is equal to 6. Not bad, right? Okay. Point P is such that OC is equal to 2/3 of OA. Interesting. And we need to find the unit vector in the direction of BC. So we have B. We need to work out C, but that is not actually that difficult. In fact, that's not difficult at all. OC is just equal to 2/3 of A. And A is 3 minus 6 and 6. So if I take 2/3 of all those numbers, that is 2 and minus 4 and plus 4. Cool. And then again, for working out the unit vector of BC, we first need to work out the vector BC, find its modulus and divide it, bish bash bosh, Bob's your uncle, easy. So BC, we take the vector C, so 2 minus 4 and 4, and we're going to subtract B from it, which is 2 minus 6 minus 7. So we get 2 minus 2 is 0. Big brain maths. Minus 4 minus minus 6 would be plus 2. 4 minus minus 7 would be 11. So now we're going to work out the modulus of BC. Now we know the total of it. That equals the square root 0 squared. Not going to bother writing it. 2 squared plus 11 squared. 11 squared is 121. Plus 4, 125, which you cannot square root, so I'm going to leave it as a square root of 125. So the unit vector of BC, again this is 4 marks, and we've done it pretty damn quickly, is you take the vector BC and you divide it by that. Considering we can't divide by square root of 125, I'm just going to leave it like this, as I mentioned in the previous question. Not bad. So 2017 wasn't a bad paper apparently for vectors. So 6 marks, and they were relatively okay. So let's keep ploughing on, but hopefully that does all make 100% sense. The next bit is where things get slightly tricky, okay? So understand the significance of all the symbols when using the equation of a straight line as expressed in the form r is a plus tb. So let's write it out one more time. And it should be noted that because they're in bold, that means they are all vectors. So this is called the vector equation for a straight line, sometimes called the Cartesian vector equation for a straight line, because you also have a parametric equation for not parametric, sorry, a polar equation for it. So that is something you need to be kind of careful of. So what do these bits mean? Well, B is simply a vector that is parallel to A. So you know you have your vector, let's say A, and B is just some random other vector. T is essentially your gradient, okay? So it's a gradient and it is a scalar, okay? A is something called a, well, you already know what it is. It's a position vector the line has to go through, okay? So if you remember, when you wanted to work out the equation of a straight line in normal terms, you would need a coordinate that the line passes through, and you'd need the gradient, right? Or you can have the gradient and the y-intercept, for example. It's essentially the same for a vector equation, okay? Except you need a vector that's parallel to a vector that the line goes through. So the line goes through A. So let's say we have A here. The line goes through it, we can call the line L, and B just has to be a vector that is parallel to that line. I know it seems like a very arbitrary set of requirements, but I promise you it does make some amount of sense. So we also need to be able to find the equation of a line given sufficient information. So if I look at this first question here, find a vector equation for the line that goes through this point and is parallel to 2i minus 4j plus 5k. This is actually remarkably easy, because they've actually given us all the information we need. B is this, A is this. Okay, and how you write it? Well, you can write it in IJK notation, or I much actually prefer to use column notation because it looks a bit more compact. But some people will, you might prefer component notation, which is completely fine. You're not wrong. 3 plus t. You don't need to work out what t is, which is a massive help, because it is actually quite difficult to work out the gradient unless you have 2 points. Obviously you can't really work it out with here, or if you have another vector, right? Question 2, find a vector equation of the line that goes through 2 points. So this is again where it gets slightly more interesting. So we have these 2 points. Let's put them like this. And the other point, I know it's not actually accurate by any means necessary, but it doesn't need to be. What we want is a vector. So remember, we do need a vector of some kind. So what we're going to do to work out the position vector is we're going to subtract them. So we're going to take this vector and minus this vector from it to work out the position vector. That will be parallel to the line, right? Because think about it. These 2 points, if I work out the kind of displacement vector between them, that will give me a vector that's parallel to the line, because the line is going through those 2 points. So a vector that's on top of the line is a parallel vector. Remember, when 2 vectors are on top of each other, that still counts as parallel. So we've got -4, -1, 3, -3, 0, -2. So this is our displacement vector. So this is the vector that is going to be parallel to our equation, to our line. And then all we need to do is sub it into the formula as we've done in the last question. And again, hopefully that makes a lot of sense. So if you need the vector and you have 2 points, if you subtract the 2 points, you'll get a displacement vector between the 2 points, which is going to be parallel to the line because it's actually going to be right on top of the line, which is handy. So you can pick whichever coordinate you want. I'm going to pick the 1, 3, 2 plus t. Done. We've got more though, because of course we've got more. We've actually got quite a bit more. I'm not going to lie to you. These next questions are pretty tricky. We need to determine whether 2 lines are parallel, intersect, or skew. So this is going to be quite important. Skew means they do not intersect and are not parallel. So remember, we're working in 3 dimensions. So if I work in 2 dimensions, this is flat plane, they can be parallel or they can intersect. Now, on a flat plane, all lines will either intersect or they'll be parallel. There are no other options, because if they're not parallel, if you trace the line back, they will cross. Right? And if they haven't crossed yet, if you continue, they will cross. But if they're parallel, they'll never cross. So all lines on a 2D plane are parallel or they intersect. However, with 3D, I can have a vector like this, right? So going like that, and a vector on top that is never going to intersect, and it's not parallel either, right? So again, you can just kind of work it as like, you have this vector going in this direction, you have a vector on top of it going in this direction. They're not actually intersecting with each other, and they're not parallel. So this is the word we use for that is they're skew, which means they do not intersect and are not parallel. So I decided to do this by showing you an equation, showing you how to prove that they are skew. Because how do you prove that something's skew? You prove that they do not intersect, and you prove that they're not parallel. So in this question, I'm actually going to show you how to prove that things intersect and are not parallel, and if they're skew. So this one question actually summarizes this whole spec point. So I thought that was really interesting. Okay. So again, to prove something skew, you have to prove separately that they do not intersect and that they're not parallel. So using this one question, you'll be able to now prove if something intersects, or if something's parallel, or if something's skew. Cool. So the line passes through these 2 points, and the straight line 2 has equation like this. So again, that's our equation of a straight line. So this is our B. Show that lines L1 and L2 are skew. Okay, the first thing you want to do is you want to write equation L1 as a equation of a line, right? So what we're going to do for L1 is, if you remember rightly, we're going to take the first kind of point as a vector, so that's going to be 0, 1, 5. And then the way we work out the parallel vector, which we call it lambda, the parallel vectors, we're going to subtract them, okay? So we have 2 minus 0, minus 2 minus 1, and 1 minus 5. Okay? So now we'll simplify this. Again, that's just the exact same as the question we've done just before. And we need to do this because just like with kind of 2D regular lines, to prove that they're parallel or intersect, we need to actually have their equation of a line. Perfect. So now I'm going to separate this into two kind of separate bits. So we're going to start with parallel. So to prove that they're not parallel, this is a 6-mark answer, and I promise you this is a beefy question. It means that the direction components are not multiples of each other. So what does this mean? Well, if you remember back in, again, GCSE, when you're proving that two vectors are parallel, what you did is, let's say you had vector A was, I'm going to make this really easy, 2, 1, and vector B was 4, 2. To prove that they're parallel, you would write one of the vectors in terms of the other vector. So I can write B as 2A, right? Because it's just twice as big. And because it's a multiple, it means that they are indeed parallel. Okay? So that's what we're going to do in this. And this is actually pretty quick. Okay? So if I write out this parallel vector, and again, don't forget, because this vector here is parallel to the overall line, if this other line is parallel to this part of the component, then it means the two lines are parallel, right? If that makes sense. So if two things are parallel and two other things are parallel to each other, then they're all parallel to each other. So if I write out just the direction components, so 2, minus 3, and 4, and I look at 1, 2, and 5, there is absolutely no constant that I can times any one of these by. It can be a fraction, it can be a decimal, it doesn't matter. That will give me to make these two equal. So the way I would write this is no constant that can multiply one vector to give the other. And that's all you'd need to write in the exam, but I'm going to say why, right? Because you probably wondered how I saw this so quickly. It's because they have different signs, right? So it'd be fine if all of these were positive and all of these were negative. But there's no constant on the face of the planet where I can change a positive into a positive, a negative into a positive, and a positive into a positive. Or vice versa, right? Negative into a negative, negative into a positive. If I'm timesing them all by the same number, they'll either all be the same sign or all be an opposite sign. But in this case, as you can see, a negative turns into a positive, but the rest of them are positive and positive. So they have all different signs. That's how I knew, okay? So that was nice and easy. So to prove that two vector lines are parallel, all you need to do is look at their direction components and see if they're multiples of each other. If they are, good, they're parallel. Nice and easy, it'll probably be a 2-mark question. So, here's where things get way more interesting. This is going to be quite beefy. So don't intersect. What we need to do, for them to intersect, the actual components themselves need to be equal, right? So 0 plus 2 lambda should equal 7 plus mu I. 7 plus mu, right? And 1 minus 3 lambda should equal 1 plus 2 mu, and so on. So that's what we have to do. And we have to prove that that the system of equations is solvable or not solvable. If it's not solvable, that means we cannot, so it means that they are not intersecting with each other. So, just to make this clear, I'll write it out one more time. I'm going to write out the actual working out and it'll make a lot more sense. So we're going to make components equal to each other. Equal. And show there's no solution. For them to not intersect, we need to show there's no solution, okay? So let's do it. If I compare the I components, we have 0 plus 2 lambda. So I'm actually going to write I, just to make this clear. And I wrote lambda, great. 2 lambda equals, for the I components of this would be 7 plus mu. Now let's look at the j's and the k's. We have here 1 minus 3 lambda equals 1 plus 2 lambda. Cool. 1 plus 2 mu. God. The k components, we have 5 plus 4 lambda (1 plus 5 mu). Okay, so if they intersect, there will be a solution to this set of equations. Okay, there'll be an actual solution. So what I mean by that is I'll have a value of lambda and mu where all of these equations will be solvable. They'll be valid. So, for example, 2 times this value would give me 7 plus the other value. 1 minus 3 of that value would also give me this, and so on. Okay? If they intersect. So if they intersect, there is a value of mu and lambda that works in all 3 of these equations. Okay? If they don't intersect, bear in mind we're proving it's skew, which means they don't intersect, right? Then there will be no value of mu and lambda that works. So essentially it'll be unsolvable. So how the hell can we prove that? Quite simple. All we need to do is try and solve it and show that there's no values that are possible. So let's get to it. I'm going to call these alpha, beta, and gamma, which again is a fairly common notation for solving these equations. And what I'm going to do is I'm going to double alpha to get mu the same, because if I double alpha, I'm going to get beta being the same. So if I do 2 alpha, I get 4 lambda, equals 14 plus 2 mu, and beta is still equal to 1 plus, careful there, 1 minus 3 lambda equals 1 plus 2 mu. And I would like to point out you can label these 1, 2, and 3 if you want. It's just like a common notation that you might see in like online resources, so I decided to use it. So if I subtract them, we get 4 minus 3 lambda, so 7 lambda. I don't know why I called it y lambda. And minus 1 is equal to 14 minus 1, which is 13. So then 7 lambda equals 14, which means lambda equals 2. So this might look quite easy so far, but just you wait. What we're going to do now is we're going to say what mu is in every single situation, okay? So we've worked out a value of lambda. Now I'm going to plug it into all 3 of these equations and work out what mu would be, okay? So for alpha, let's start with alpha. Alright, so alpha is 7 plus mu equals 2 times lambda, so equals 4. So mu is equal to minus 3. Okay, that's one solution. Then with beta, what do I get? 1 minus 6 equals 1 plus 2 mu. So minus 5. Lord, that struggled. So then, interesting, mu equals minus 3. So far they're both the same. So that's actually good, that's a good sign. But you need to check all 3. So let's keep doing it. 5 plus 8 equals 1 plus 5 mu. I'm so paranoid about getting things wrong. Okay, 1 plus 8 would be 13. And then minus 1, so it would be 12 equals 5 mu. So mu is equal to 12 over 5, which is not correct. So, in short, there is no solution as equations are inconsistent. No solution as equations are inconsistent. Therefore, no intersection. Okay, and you'd find that if you were to work out lambda in a different way, you'd actually get a different value of lambda too. So that is actually another way to do it. So they don't intersect, so not parallel, and don't intersect. Therefore, they are skew. Now that was fun, right? And we're finished with that for now. We're finished with that part. Part 2, find the acute angle. So we've got another thing to do. Look at that 6 marker, man. Oh, perfect. I like it when you have to write sentences in a 6 marker, right? So find the acute angle between the direction of the line L2 and the direction of the x-axis. So what we're going to do is, well, actually, let me point this out. So the equation for the x-axis, right? So if I were to get like an equation of a straight line for the x-axis, is that the only point it passes through is, well, it's not the only point, but it passes through the origin, right? 0, 0, 0. And then plus some lambda. And what is the direction component? Well, it's only 1 in the I component, so it's 1, 0, 0. Okay, so this is the equation for the x-axis. For y-axis, it would be 0, 0, 0 plus lambda 0, 1, 0, and so on. So what we can do here is compare the directions of the x-axis with the direction for L2. So direction for L2 is just going to be the direction component of the second line, which is this one. So it's 1, 2, 5. And I'm actually going to call this A with a hat, just to make my life slightly easier. And direction of the x-axis, which I'm going to call B with a little hat, is equal to just 1, 0, 0. So we're finding the angle between both of these direction components. So the best way to do that is using the dot product. Okay. So again, the definition of a dot product is cos alpha. So cos of the angle between the two components will be the multiplication of the two unit vectors over the magnitudes of both vectors. Cool. So if we work out the dot product first, so the dot product is quite simply going to be the multiplication of both of them. So 1 times 1 plus 2 times 0 plus 0 times 0. I'll write it out, but it's just going to be the same thing. Over the magnitudes of them, so 1 squared plus 2 squared plus 5 squared plus, again, the only magnitude we care about would be 1 squared, so it'd just be 1, shockingly. And what we can do there is actually work out what it is. So that's just going to be 1 over 1, 5, 30, 36. So 1 over square root 30. Cool. So then alpha is just going to be equal to the inverse cos 1 over root 30, which you should find is 79.5, which is an acute angle, so we're already done. And that brings us to the end of the vectors topic. It's incredibly beefy. It's quite long, but just looking at the video, it's 48 minutes long. We're going to cut it there. So I wish you the best of luck, and I'll see you in the next one.